If it gets too cold, feel free to. I think we need this fresh air though. Okay, so big things: expanding and condensing. So we have exponent laws that you guys know pretty well, and since exponents and logs are related, I'm going to talk about them. But with exponents, we condense. If two things are being multiplied, two common bases are being multiplied, we condense it by adding their exponents. So there's a link between multiplication and addition. And we're going to find the same is true in the log rules. So this one we're actually going to expand. Right now it's a single log, but it's a single log of the product of two things. We're going to expand that into two separate logs that are going to be added together. So again, this multiplication will link to addition. This is going to be log base b of x plus log base b of y. And we'll see over today, sometimes you're asked to condense, sometimes you're asked to expand. So you can use this in either order. You can go from right when they're expanded to the left and condense it, or the way we did it, which was it was already condensed and we expanded. You'll see over the next few days when is appropriate to do either one. As far as the second log one, which is division, single log, and things are being divided. Division, as you remember from exponent rules, ties with subtraction. So the division of common bases turns into subtraction. So there's that link between division and subtraction. So this division, when we expand the log, is going to turn into subtraction. Log base b of x minus log base b of y. This is a little more of a stretch, but we all know from exponents that power to power means multiply. With a log, this doesn't really expand into two logs, but this is really the main property that's going to make logs so useful, is that if you have log base b of an x to a y power, whatever that power is comes out in front as a coefficient. So it's y times log base b of x. And that one's going to be the one that allows us to solve, kind of unlocks this whole ability to solve exponential equations. Because right now, if you remember, the only exponential equations we can solve are when, where did we do it? Oh, I don't have it near to me. Or when the bases are the same on both sides. So right now we can only solve 5 to the x power equals 25 to the 2x power. When we can create the same base on the both sides, we would make this a 5 squared. Those are the only ones that we conveniently can solve right now. This property is going to allow us to solve a lot more than that. All right, so in this one, log base 3 of 9x. So Jason, which property, 1, 2, or 3, would apply to log base 3 of 9 times x?
That'd be
1. Right, because 9 is being multiplied by x. So if we were to expand this, it'd be log base 3 of 9 plus log base 3 of x. And part of that we can evaluate. If we think of that log from the what power perception, Angie, what's log base 3 of 9? Think of log as the what power function. The base of 3 to what power would give you 9? The second. Very good. Or change a base formula. Log base 3 of 9, you can type in log of 9 divided by log of 3, 2. So that portion of it is just 2 plus log base 3 of x, and there's your answer. Okay, Morgan, on number 2, which property is going to be used here to expand this? 1, 2, or 3? The second one, the division. Can you expand it for me? What would you write?
Well, isn't it, if there's no base, it's just automatically 10?
Yep, very good. Good memory. There's no so we don't even actually have to say it, because if there is no base and we keep writing it without a base, it'll still be 10.
Log times x squared
Yep.
minus log times 1,000.
Yep. You said it wrong, but I think I know what you mean. You just can't say times. It's not log times x squared, because log's not a number. It's the log of x squared minus the log of 1,000. And then this one, like she said, base of 10, 10 to what power gives you 1,000, Vince? 3. Now, did you type in log of 1,000 on your calculator, or did you do the change of base formula? Right. In this one, you don't need the change of base formula because it is the base of 10. So that would be where we are, but that's not an option. Why not? Because we're taking...
Oh, just because it's raised by power.
Right, because we're taking the log of something that has a power. So what do we do with that? Go ahead.
Put it in front, so it's just like 2 log of x.
Very good. 2 log of x minus 3, which is option 1. So there we saw a combo of 2 properties in one problem, which happens. They kind of unravel slowly. You're not going to just throw 5 properties and apply them all at the same time. You take it kind of one at a time, and then as they unravel, you use each additional property as needed. Okie doke? Now, in exercise 3, this is a great way that the Common Core would get around the fact that you can't just type in log 12. Because the way that they're phrasing this, it's not going to work out that way. So they force you by saying, if A is log 3 and B is log 2, which of the following correctly expresses the value of log 12? So what we know about is the log of 3 and the log of 2. They gave us values, sort of, for those. So we need to really break down our 12 into 3s and 2s so that we can use the fact that log 3 equals A and log 2 equals B. I'm going to do that by making log of 12 the log of... A couple ways I can do this. I could do 2 times 2 times 3. Or I could just do the log of 4 times 3, which I'll do that second, just to kind of show you the 2 different options. So in the first one, 2 times 2 times 3 is an okay substitution for 12. Our property of changing multiplication into what operation, Owen? Changing multiplication. If I'm expanding this becomes the log of... Right, it's a single log right now, so which property are we going to apply here?
The first one?
The first one. So the log of things being multiplied turns into...
Log. X.
Well, it's not an X, it's a 2.
Log 2.
Okay, well, let's go back to operations. We're looking right now at the log, a single log of multiplications. Agreed? Single log of multiplications. Agreed? It splits into a bunch of logs being what operation?
Addition.
Added. So log of 2 plus log of 2 plus log of 3. Does that make sense? Oh, does that make sense? And then, again, they didn't give us the actual values for those, but they gave us variable values. Log of 2 equals b, so that would be b plus a. Which is, which option?
Four.
Yeah, b plus b is 2b, not b squared. That would be 4. So just watch on the second one how this unfolds. Because initially this is log of 4 plus the log of 3. But the log of 4 they didn't tell me. The reason 4 works, though, is because it's the same as the log of 2 squared. Does everybody see that? And then because there's that number being squared, I can take that exponent out in front. So it's 2 times the log of 2 plus the log of 3. And the log of 2, they told me, was b, so there's 2b. Plus the log of 3 is a, so there's 2b plus a. Same thing unfolds. Just kind of done differently. Does that make sense? All right, exercise 4. Which property should we first apply? Log base 2 of this, what would you say, Eric? Are we applying 1, 2, or 3? 2. The division turns into? Log of 2 things being divided turns into multiple logs being subtracted. So that would be log base 2 of root x minus log base 2 of y to the 5th. Then what property can be applied? What do you think, Elena? Do we have log of multiplication anywhere, log of division anywhere, or log with an exponent anywhere?
Oh, the power.
Yeah. On which term, first or second?
Second.
The second for sure. So what would this turn into?
Maybe 5 times the log of 2y.
Yep, that 5 would go right out in front, so that would be minus 5 log base 2 of y. And so if you look at your options, 1, 3, and 4 all have that, minus 5 log base 2 of y. So that's out. None of them look quite like that. But when you take the square root of x, that's the same as raising x to what power? The 1/2. And now, it didn't appear like it was an exponent rule, but a radical is an exponent. So now it is an exponent of 1/2. That 1/2 can come out in front of its term. So make sure we understand that radicals are exponents. And then it's option 3. Okay, that was all of that was expanding. Multiplication into addition, division into subtraction, and exponents into kind of coefficients. Any questions so far? Okay. More expanding. We'll come back to that one in a minute. Exercise 6. This gives us f of x as a function and g of x as a function. Asks us to do a composition. F of g of x. So what's the mechanics here? What do we do? Lucas?
Let's solve it for g of x and then plug that value in for f of x.
Right, which we could do if it was like f of g of 5. We would find g of 5 first, is what you're saying. Solve it for g of 5, and then take that number and plug it in for f of whatever that number is. If it's not a number, though, we just have to take that whole function, the whole 100x cubed, and plug it into the f function. Right? Remember this? So we're taking the g of x function, which is 100x cubed, plugging it into the f of x function. So that'll be log of 100x cubed. And then what property should we apply first to expand this? Multiplication, division, or exponent? What do you think, Haley? Multiplication. So what does it split into?
Log of
What are the two things being multiplied? 100 times x cubed.
Okay, so log of 100 plus log of x cubed.
Very good. Now, log of 100, we can evaluate because the base is 10. And 10 to what power gives you 100? Georgia? 2. And then on the second term, what rule can we apply? Jack B. Put the 3 out in front. Very good. Plus 3 log of x. And that's option 4. So they kind of combine your log rules with your function composition stuff. Okay, number 7 orders things a little bit differently. We're not taking the log of something times something right off the bat. There's definitely multiplication within there. But on the outset, this is the log base 2 of 32x to the 7th being raised to the 1/2 power. So that radical being around the whole thing kind of trumps it from an order of operations standpoint, where that exponent is the first thing we have to address. That 1/2 has to come out in front. So that'll be 1/2 log base 2 of 32x to the 7th. And once we break into that radical by doing that, now we can focus on the multiplication. The 32 times the x to the 7th splitting into addition. So that is log base 2 of 32 plus log base 2 of x to the 7th. Now, all of that had the 1/2 out in front. So because we created a binomial when we split that, we have to keep that binomial in parentheses because there was that 1/2 out in front. And then once we're into there with the log base 2 of 32, we can just make that 5. And this one, we can just bring the 7 out in front. And which answer equates to that? 2, right? Having the whole thing divided by 2 is the same as having a 1/2 out in front. Good. Okay, exercise 8 asks us to evaluate the log of 4,900 in terms of k. 4,900, given that they've told us only about log of 7, we want to break this thing down into 7 somehow. So 4,900, we all can agree is 49 times 100. Is that fair? And since they told us about the log of 7, I'm going to actually make 49 7 squared. Now I'm going to split the multiplication into addition. I can't throw in that log of 7 equaling k yet because it's not log of just 7 right now. It's log of 7 squared. So that 2 has to come out in front. Now I have log of 7, so I can replace it with k. And with no base written, we assume it's 10. Log base 10 of 100 is what? 2. 10 to what power is 100? 2. So 2k plus 2. Which answer there is the same as 2k plus 2? 1. Okay, doke.